Okay, so welcome back, everyone. We continue with Thorsten Heidersdorf from Newcastle, and here is about fusion rules for the general linear and orthosymplectic supergroup.
So thanks a lot for the opportunity to speak here. So this is some kind of overview talk about fusion rules. In other words, it's about the question: how can you decompose the tensor product of two representations into indecomposable representations? And basically, let me state one main theorem right away. And so, in the tradition of this place here, it's in what Google thinks is Gaelic. Actually, you can still figure it out because the Gaelic language apparently didn't have any words for Kovanov's arc algebra nor for orthosymplectic supergroup. I don't know if that led to its downfall in the 20th century, but so it's apparently a talk that involves an algebra called Kovanov's arc algebra, which deals with decomposition of tensor powers, and it involves the orthosymplectic supergroup. I think the English version wouldn't, at that moment, not make much more sense. So I'll devote the rest of the talk to explain that thing. Okay, let me travel back in time to classical theory 100 years ago. So I take a semi-simple Lie algebra. Actually, I would also like to take GLN, which is not semi-simple. But if I talk about GLN, I would only consider algebraic representations of GLN. So those who live to the algebraic group GLN, and then that's still a semi-simple representation category. Yeah, so while it says, okay, in this situation, every representation is completely reducible, the C representation here means automatically finite dimensional for me throughout the whole talk. And so then there are some key theorems which you are, I think, all know. So we can classify the irreducible representations nicely by things called height weights. And then there is a wild character formula for the character of such an irreducible representation. And one nice thing that you can use the character for is that you can use it to determine these fusion rules. So if you take two irreducible representations indexed by highest weights lambda and mu, you can take L lambda times L mu, and you can basically find the decomposition into irreducible representations L nu. And in case you take SLN or GLN, then you get the so-called Littlewood-Richardson rule. It's a combinatorial rule that describes these coefficients here, C lambda mu nu. So that is kind of classical, but by no means trivial. And so it's a problem that has sort of implications beyond representation theory. Finding such fusion rules has applications in physics. Usually these tensor product rules have geometric or topological meaning. For instance, if you take a Grassmannian, it comes with something called a Schubert stratification, or you can talk about Schubert classes in the cohomology, and the coproducts in the cohomology are computed by the same rule, and so on and so on. Or if you go to if you quantize the whole picture, you talk about quantum link invariance, and these tensor structures play a big role. So this is all classical, and basically what we want to do is we want to replace the semi-simple Lie algebra by a super algebra, a Lie super algebra, or maybe an algebraic supergroup, and study the same problem, but it's much harder, and we don't know a lot about it at the moment. So historically, these super objects have two main sources. So of course, physics. The keyword might be supersymmetry, whether this has anything to do with physics is another question. Or you also see Z2 graded structures in topology. But what happens there, if first of all, for instance, if you just look at the definition, not a lot is going to happen. I mean, the vector space is replaced by super vector space, so just a Z2 graded vector space. The algebra is replaced by super algebra, just Z2 graded algebra. Well, you can generalize the Lie algebra pretty quickly to a Lie super algebra. It's just something Z2 graded, which involves some sign factors in these skew symmetry and the Jacobi identity. So all the initial definitions look pretty much like in the classical part, and looks a bit boring. But then when you actually want to do representation theory, you see that The huge difference is that Weil's complete reducibility theorem completely fails. So you're leaving the semi-simple world and you're going to the non-semi-simple world. So in particular, even if you're just interested in this problem of finding these fusion rules, the issue is that you are not going to get a decomposition into irreducible representations, but only into indecomposable representations, which are maybe very hard to understand. And so in general, if you look at this representation theory of Lie supergroups, algebraic supergroups, Lie superalgebras, in the techniques that we used or in flavor, it's much closer to, say, modular representation theory or theory of quantum groups than maybe the classical theory. Okay, so here are two examples of supergroups in a sense. I mean, Pavel did all the work for me. He already defined these things. But let me just take two examples. So I defined a supergroup in a slightly abstract way, basically factorial, like you would define an algebraic group. So an algebraic group could be seen as a representable functor from commutative algebras to groups. And so here GLMN can be defined in the same way. You take a commutative superalgebra. So superalgebra is just that two graded. Commutative means commutative in the super sense. So the Grassmann algebra would suddenly be commutative in this world. And then you take this superalgebra A and you assign to it the invertible even matrices in sort of these MN matrices. So I think of these matrices as like block matrices, A, B, C, D. A is an M times M, B is an M times N, C is an N times M, and D is an N times M matrix. Even means that if you look at A and D, the entries in your matrix are from A0, the even part of A, and the CD entries are from A1. Another supergroup that you could define is the following, which sort of takes the orthogonal group and the symplectic groups and turns it into one object, the orthosymplectic supergroup. You just look at all the matrices in GLM2N, which preserve that form, which is given by this big matrix there. If you would set Jm equal to 0, you would just recover the orthogonal group. If you would set the 1m part to 0, then you would just recover the symplectic group. But here in the superworld, you can mix them. And the ST here just stands for transpose. It's basically like in the classical world, it's a transpose with sign factors thrown in. This is OSPM to N. Again, if you put M equal to 0, that's just a symplectic group SP to N. If you set N equal to 0, that's just the orthogonal group OM. And then rep OSPM to N, that's the category of finite dimensional algebraic representations of this group. If you go back to the talk of Pavel, he would say, okay, you can take the coordinate ring of these algebraic supergroups. This is a superhop algebra, and then you can talk about co-modules over this superhop algebra, and that's this representation category. So that would be his point of view. Here's an example of representation. You have an analog of a standard representation or a natural representation. You just take C to the M to N. So as a vector space, it's just C to the M plus C to the 2N. But now you just say, okay, the first part is even, the second part is odd. And so it becomes a Z2 graded vector space. And then you have an action of OSPM to N on this standard representation. If you would take GLMN, you could, of course, just take C to the MN. And then you can do the usual things that you can always do with representations. You can then direct sums and tensor products and quotients and whatever. Okay, so I already said initially when you start doing representation theory for these super things, then many things are similar to the classical theory. So for instance, you can still classify irreducible representations by highest weights. So here's an example. You take GLMN, and then well, I should be careful here when I talk about irreducible representations. So representations are always algebraic representations. Not I'm working with the algebraic group, not the Lie algebra. That's why you see only integral coefficients here. So then these irreducible representations are parameterized by these tuples lambda 1 to lambda m, and then the second tuple lambda m plus 1 to lambda m plus n. and so both satisfy the usual sort of dominance condition for weights of GLM or GLM. That's not very surprising, by the way. If you look at GLMN, if you think of GLMN as Bloch matrices, then so A, B, C, D, and if you set B and C equal to 0, we see that GLM times GLN sits inside GLMN, and in particular GLM times GLN and this big GLMN share the same diagonal matrices. And you know from classical theory that an irreducible representation is determined by what it does, determined by the diagonal matrices, how they act. And since well, they share the same Cartan or whatever, torus or diagonal matrices, you get the same irreducible representations in some sense. Now the big difference, as I already mentioned, and here's a precise statement, if you have a supergroup which has semi-simple representation category, then it's a product of reductive groups or together with so-called OSP 1 to N. So if you go back to this previous slide, I defined OSP M to N, and M has to be equal to 1 in order for you to have a semi-simple representation category. This is essentially proved by Djokovic and Hochschild in the 70s. Okay, now, despite all this, I would say that nowadays we have a reasonably good understanding of the structure of rep G. G here is some supergroup. Maybe I should impose some conditions on G so that the statement is really true. As an abelian category, so it means that you can somehow say, how do the blocks look like? How do the X1 between irreducible objects look like? Sometimes we have formulas for the super dimension. We have sort of character formulas, but they're pretty awful. But still, especially if you take GLMN or if you take OSPM to N, then we know a good deal about this category. What we really don't understand is the monoidal structure. So it's a question for fusion rules. I'm not even talking about fusion rules like the Littlewood-Richardson rule or the nose. You could even ask like more structural questions like what are the tensor ideals or things like this. And as tensor categories, these categories rep G are widely not understood. Okay, so let me mention some positive results that we know. So at least in the case for GLMN, people computed the so-called Balmer spectrum of the stable category of GLMN, which in some sense gives an abstract way to think about the classification of tensor ideals. There's a very recent work which says, okay, there's something fancy called geometric supersata K, which basically says, okay, rep GLMN is equivalent as a tensor category to some category of purpose sheaves on some space, which becomes a tensor category by a convolution of purpose sheaves. There's also, so that's different from a real fusion rule, but there are truncated fusion rules. And if you, so Pavel mentioned this already in his talk. So when you semi-simplify a category, you're basically throwing away all these indecomposable representations of vanishing dimension. Here, the relevant dimension, the super case, is the super dimension. So that's the dimension of the even part minus the dimension of the odd part. Yeah, so the representation is a super vector space. It has an even and an odd part, and you take the difference of the dimensions. So if you throw away all indecomposable representations of super dimension 0, which is somehow the generic situation, so most representations have super dimension 0, then you can actually find fusion rules for these truncated parts. By understanding the semi-simplification. But today I want to study really the question, when can you have fusion rules that are really like the Littlewood-Richardson rule? And then the answer is that our understanding is very limited. The only known cases, if you look at all possible supergroups, are basically the following two. So you take V and W, and you take GLMN, and then you say, okay, V and W should be direct summons in some mixed tensor power of the natural representation of GLMN. So here, V is a natural representation, and then V check, that's a dual. Then you let R and S run to infinity, and you look at all possible direct summons. And if you find two such direct summons, then we know exactly how to decompose V tensor W. So there's really an explicit rule, like the Littlewood-Richardson rule, that does the computation, just that it's really decomposition into indecomposable summons. I mean, it is considerably more complicated than the Littlewood-Richardson rule, but it is at the end something explicit, and you really can say, okay, here's an indecomposable summon, and it looks exactly like this, and these are its composition factors and whatsoever. And the second case in which we know the answer is if you take the orthosymplectic supergroup and you take now direct summons in V tensor R, where V is the natural representation. And note that it's basically the same as the first case because the natural representation of OSP is self-dual. So this behaves like mixed tensor powers in that sense. Okay, I want to explain today how you get this result for the OSP case. The GLMN case was done previously, and it's exactly the same basic strategy. So there were preliminary results by Denker, Rieschaler, and Rahm, maybe the 90s, and maybe 10 years ago by Lehrer and Zhang. Then even maybe 7, 8 years ago already, there was work by Johnny Combs and myself using so-called Deligne categories. That's also something that Pavel mentioned. Basically, he has already done my work. And then there are newer results by Nehme, Stroppel, and myself that explain basically how these indecomposable summons look like that come up in a decomposition of tensor products. So I don't want to spend too much work on these Deligne categories, just 1 or 2 slides, and this is very philosophical, basically. So instead of a precise statement, here's a picture. You see this OSP or rep OSP category can basically be squeezed into 2 much easier categories. So here on the bottom, you have representation of a symplectic group or representation of the orthogonal group. And above, what you have is a 1-parameter family of tensor categories or symmetric monoid categories. They're parameterized by the natural numbers, and I call these categories rep OT. And these were first defined by Deligne, and sometimes is also called Deligne category. So for each complex number, you have a symmetric monoid category. And if your complex number T happens to be actually integer, then these categories they have connections to classical representation categories. So basically, these categories rep OT and rep SPT, when T is an integer, arise as quotients of these interpolation categories. That's why the name interpolation category is there. But before you go from this Deligne categories down to rep OT or rep SPT, you pass through rep OSP, M to N. T here is M minus 12. And so, why is this relevant for this problem of decomposing tensor powers? Well, for 2 reasons. First of all, this functor M to N basically is made up in the following way. These Deligne categories rep OT, they're generated by an analog of the standard or natural representation. And this has dimension M minus 2N. And under this functor M to N, it maps to the natural representation of OSP M to N. Now, this functor F M to N, it's a tensor functor. That means F of X tensor Y is the same as F of X times the tensor F of Y. And so it's compatible with tensor products. That means if you're in the Deligne category, if you take this analog of the natural representation, you take its tensor powers, the functor will send these into the tensor powers for OSP. And this functor, and I will talk about this on the next slide, will send indecomposable objects to indecomposable objects and direct sums to direct sums. And so basically you can study this behavior of V tensor R in its decomposition in this Deligne category.
Is it exact one?
No, it's not exact. So this functor, so basically these the link categories are much better understood than OSP. And you can use them, well, you can answer questions about OSP and these link categories, and then use the functor Fm to n to push the information down to this very complicated category of OSP. The disadvantage is that you only see basically what happens for V tensor R. So the image of this functor Fm to n is rather small. It doesn't see most of the representation of OSP. It only sees those that are direct summands in V tensor R for some tensor power. So that's why, if you go back to this statement here, that we only understand these cases, the reason is that in the GL case or in the O case, these delete categories only see these modules that come out in this way. Okay, so the main statement that you need to know about this functor Fm to n, that's the following. First of all, in the delete category, you can classify the indecomposable objects, and they're just parameterized by the set of all partitions. That's the big lambda there. And then you know the indecomposable object corresponding to a partition lambda by R lambda. And then if you look at the images of the R lambda, well, the set of R lambda which aren't killed by Fm to n, that's a complete set of pairwise non-isomorphic indecomposable summands in tensor powers V tensor R as R ranges to infinity. And you can also precisely say when this module is non-zero, there's basically a combinatorial measure for the size of a partition which shouldn't be too big. I won't define it here. Okay, so what it gives you is a classification of the indecomposable summands that come up in V tensor R, for any R. So then I'm just a bit sloppy. I'm just saying that in the delete category, we know actually how to decompose R lambda to tensor R mu. Basically, it looks a bit similar to an O infinity rule when you take the limit over all ONs. And then you can use that Fm to n as a tensor functor to say how are the images of the R lambda and the R mu. How is Fm to n of R lambda tensor Fm to n R mu decomposing? The disadvantage of this result is basically that it doesn't tell you how the R lambda look like. It's more like, okay, you have some indecomposable objects and they're parameterized here by these partitions that are not too big, but you don't know what do they look like? I mean, what is their Stroppel filtration? What are the composition factors? When are they irreducible? Whatever. And it seems impossible from this approach to answer this question. And so there is basically the new theorem says exactly how these Fm to n or lambda look like. So we can explicitly describe the Stroppel filtration and the composition factors of these indecomposable summands that arise. And basically what it uses is something called Kovanov's algebra for OSP. And I'm not going to give a definition here. If you've ever seen these Kovanov algebras, you will understand why. Basically, but let me just give you a philosophical idea how these Kovanov algebras look like. Well, the Kovanov algebra is basically arises in the following way. So you look at all the projective covers of all irreducible representations L lambda, and then you form that's okay. So then you look at something called the locally finite endomorphism algebra of P, of this giant representation. And then by Morita theory, this category, rep OSP M to N, which I denote by F, that's equivalent as an abelian category to the modules over this locally finite endomorphism algebra. So that's abstract nonsense and completely useless unless you find the miraculous way to really describe this endomorphism algebra explicitly. And so there was a preliminary result for OSP, namely due to Eric and Stroppel, who basically constructed a diagram algebra, which they call a Kovanov algebra of type B, together with an explicit ideal, such that this locally finite endomorphism algebra is actually equivalent is isomorphic to this algebra K over I. And so that means that if you want to just understand this category rep OSP M2N as an abelian category, so questions about blocks or X1, you can try to work in these modules over the diagram algebra, and this is much more manageable. So I mentioned earlier on that we have nowadays a reasonably good understanding of these abelian categories that usually comes from such theorems. So there are analogous theorems for GLMN, for instance. So modules over this diagram algebra can be understood much easier than representations of these supergroups. The question is a little bit, I mean, this is just an abelian categories. It's not an equivalence of tensor categories. So why can we say anything about tensor powers or direct sums and tensor powers using these Kovalov algebras? I'll come to this in a second. I'll skip this here. But here's basically, I just wanted to give you a picture of how these Kovalov algebras look like. When I say diagram algebra, what does it mean? So basically you have like a number line, and you have certain symbols up and down on the number line, and then you form like little half circles of these number lines. You can have upper circles or lower circles called caps or cups. And what you see here, and then you take basically a cap diagram. So these are the half circles which go up, and you take a cup diagram. This is a diagram involving these lower circles, and then you glue them on top of each other. And here you see two in the upper left, and now we want to multiply them because this Kovalov algebra will be basically a graded associative algebra whose basis is given by such glued diagrams. When you glue a cap diagram on top of a cup diagram, and there's some compatibility between the pictures, then you call it an oriented circle diagram. And the underlying vector space has just the basis, the underlying these oriented circle diagrams. And then there's a complicated surgery procedure to multiply two such diagrams. You see it here in two examples. Basically, once you are at the upper right picture, basically what you do is you collapse the middle completely, and then you have again an oriented circle diagram. Okay, that's just a nice picture. This is this Kovalov algebra, and what you can do now is, instead of talking about tensoring with V, you can, that's a standard representation or natural representation, you can decompose it into so-called translation functors. Basically tensor with V, and then you project on all the possible blocks. Or in fact, you project onto the summand, which changes the generalized eigenvalue of something called the Casimir operator by a precise value. And so when you think about V tensor R, one way to think about this is that this is just a composition of all these translation functors theta I, all these projections onto direct sums which change the eigenvalue of the Casimir operator by a certain prescribed value. And you apply this to the trivial representation. And now these theta I, these translation functors, they can exactly be modeled on the side of these Kovalov modules. And then they're called big theta I. And the upshot is that we can exactly calculate what do these modules theta I do on for these modules over the diagram algebra. And basically what you have to prove is just that this equivalence of categories between modules over this Kovalov algebra and representation of OSP is compatible with these two types of functors. On the one hand, you have the translation functors for OSP. On the other hand, you have the theta I's. And this is just this equivalence of categories that you have between modules of the Kovalov algebra and representation of OSP that intertwines these two different functors. And so when you have that, then you're done, because then you can really calculate the structure of V tensor R in its direct sum by doing everything on the Kovalov side, where you can calculate really everything in diagrammatic terms, and then you throw it over to OSP once you're done. And the second application is that this result also will exactly describe the effect of translation bunkers, so these theta i's, on irreducible and projective representations. And the reason is simply that we can do this for on the Kowanov side, and then again we use the equivalence of categories and the compatibility with these two functors to answer the question. And at the end, what you see, so I won't really explain what is written here. At the end, you will see that, okay, we can exactly describe how these indecomposable modules look like. They are tensor product decomposition that's already governed by the Deligne category, but now we know exactly what the summons are. If you go back to the problem that I stated in the beginning, the question was for the tensor product decomposition between two irreducible modules, L lambda tensor L mu. You can ask, is that helpful here? I mean, which irreducible representations come up actually as direct sums in such a tensor power? And then the answer is both very satisfactory and very unsatisfactory. Every block has a unique irreducible R lambda. So blocks can either have one element, namely exactly if L lambda is projective, that's a generic case. So this gives generic tensor product decomposition or fusion rules. But if L lambda is not projective, a block will have infinitely many irreducible representations, and you see exactly one comes up. So from that point of view, it's very, very unsatisfactory. We are very far from getting general fusion rules via this method. Okay, I think that's what I had to say. Let me end with two advertisements very briefly. If you feel like, okay, this is maybe something interesting, you can come to Bonn and get representations of supergroups. I know this is a bit short because it's in 1.5 weeks, but still. That might be a thing. Or much closer to here, you can go to RT62 in Newcastle in September. So I wanted to advertise these two things at the end. I'm not sure we're talking here about super, but it's super close maybe for some of you. Thank you.
Thank you very much. Questions?
Can you go back 2 more slides to the results? Thank you.
Which one?
That one. So is there a good reason why these things are self-dual?
I mean, all indecomposable. So all direct summaries in V tensor R are self-dual. That's, I mean, the standard representation is self-dual. It doesn't automatically imply that they're actually self-dual, but it maybe suggests
It makes it possible.
Yeah.
And so you don't think this is a general feature. This is something that's probably specific to
That's very specific to these direct summons that appear here in V tensor R. So we understand very little about tensor product decomposition outside of these of this case. But what we see in the few cases where you can maybe calculate something by brute force or so, the structure that you see here is not a good guide for the general situation. For instance, these direct summons that come up, they have always simple top and simple socket. And you see already, like in a few sampling computations for GL22, this socket and top can be arbitrarily big.
Okay.
So, and many other things fail in the general case.
And how good a control is the repeating category? I know you're talking about before you want to do the monoidal stuff now, but I'm also curious about repeating category. Is this like wild, or is there like a classification of the decomposables, or how?
So in most cases, usually the representation categories are wild. So there's a notion. So if you take an irreducible representation L lambda, there's a notion of so-called atypicality, which is a certain number you can assign to this weight lambda. If the atypicality is 0 or 1, then the block is tame. So then you can classify the indecomposable representations, and in all cases where this, which are possible, it has been done. You can really write down the quiver and the relations of the quiver, and it's pretty manageable to write down the indecomposable representation. Now, if the atypicality is 2 or bigger, the blocks are always wild. And then, of course, there's no hope of classifying in decomposables. That's certainly part of the problem here, why we don't know so much about these fusion rules, because I mean, it's impossible to classify decomposables or to make any good guesses which ones come up.
What level of atypicality is the standard representation?
Depends on M and N. So it's usually, if M is different from N, it's actually sort of the highest atypicality. So I mean, for instance, the principal block, so there's always the highest atypicality. Every block will be equivalent to the principal block, some other group. And so in a sense, if you want to understand the classification of indecomposables, or I mean, what types of blocks are possible, you can always specialize to the principal block of some group. Yes. When I said for GLMN and OSPM2N, we understand somehow the X1s between irreducibles. What it means that, at least in theory, maybe not in practice, you can calculate the underlying X square. You can't calculate the relations. Okay.
If not, that's fine. Let's begin again.